Okay, so here are the topics that we talked about in Chapter 3. We talked about formula mass, we talked about molar mass, we talked a little bit about the mole, particularly how to look at a particular molecule and make a mole ratio, look at the atoms, the number of atoms. And we also talked about mass percent and finding molecular formulas. In finding molecular formulas, we also talked about empirical formulas, and we talked about how we could use combustion analysis data in order to determine molecular formulas. We also talked about writing and balancing chemical equations, which I forgot to write on this topics list. But for the end of Chapter 3, you should be familiar with all of these concepts, and we're going to review them one by one. Okay, so let's review formula mass and molar mass first. So formula mass is just the mass of an individual substance, like molecule or something that formula unit, so something that's covalently bonded or something that's ionically bonded. You find the formula mass the same way. And we also call this the molecular mass or the molecular weight. It's the sum of all of the atoms for whatever substance you're interested in. And in contrast, the molar mass of a compound is the mass in grams of 1 mole of whatever the substance that is, either a molecule or a formula unit, something that is covalently or ionically bonded. And it's numerically equal to the formula mass. So let's calculate the formula mass of calcium nitrate. So first of all, you have to remember how to write the chemical formula from the chemical name. So to do this, if you look from the periodic table, you have calcium. Calcium has a 2+ charge on it. Nitrate is NO3. Nitrate has a 1- charge on it. So you need 2 nitrates for every 1 calcium. So the chemical formula for this is CaNO3,2. Now that we know the chemical formula, we can calculate the formula mass. So from the periodic table, I'm just going to put, and formula mass is also called formula weight. So I'm going to put the formula mass is equal to, we have 40.08 for calcium from the periodic table. There's 2 nitrogens in this compound, so 2 times, it's 14.01 AMU, plus there are 6 oxygens, 6 times 16 AMU. I'm going to put parentheses like that. Alright, so put that in your calculator. We have 40.08 plus 2 times 14 plus 6 times 16 is 164.08. And then I put the units as AMU since it's a formula mass. If we wanted to know the molar mass of calcium nitrate, it would just be 164.08 grams per mole. Okay, because they're numerically the same. All right, let's go to the next topic. Okay, the next thing we talked about was using molar mass to count molecules. This is similar to what we did in the earlier part of Chapter 3 or even the end of Chapter 2, where we used the molar mass or the atomic weight to find the number of atoms. So we're doing that, but with molecules in this chapter. So we're using the molar mass to convert whatever amount that we have into moles, and then using Avogadro's number to calculate the number of molecules. And so here's sort of a roadmap for this. So if you have grams of something, you can find the moles of it using the molar mass or formula mass. Well, you can't use the formula, but you can use the molar mass. And then you can find the molecules using Avogadro's number. Alright, so just like we've been mapping out in class. So let's practice that. If we want to find the number of ibuprofen molecules in a particular tablet of ibuprofen, we can start with the mass. We can calculate the molecular weight of ibuprofen, and then we can find out the number of moles. One thing to notice is that the mass is in milligrams, so we'll have to convert from grams or 2 grams first. So let's do that. So if we have 200 milligrams of ibuprofen, for every 1,000 milligrams, there's 1 gram. I'm going to calculate the molar mass really quick. Okay, the molar mass is 197.008. Oops. I'm going to label this C13H8O2. My stylus isn't working very well. I'm not sure why. Alright. Now we can go from moles to molecules. So for every 1 mole of C13H8O2, there's going to be 6.022 times 10 to the 23rd molecules. I'm going to make sure to label this. Alright, so let's put this in the calculator. 200 divided by 1,000. 6.022 10 to the 23rd. Alright, so we should get 6.11 times 10 to the 26 molecules of C13H8O2. So that's kind of interesting. I mean, in one ibuprofen tablet, there are that many molecules. So next time you take ibuprofen, you can think of that. Okay, so let's look at the next problem. So this one, you want to find the amount of chloride ions in a particular amount of moles of aluminum chloride. So the first thing is we need to identify the chemical formula for aluminum chloride. So aluminum has a 3+ charge on it. Chloride has a 1- charge on it. So for every 1 aluminum, there are going to be 3 chloride ions bonded to it. Okay, and so if we want to make a mole ratio here, for every 1 mole of aluminum chloride, how many chloride ions does it take? Well, for every 1 mole of aluminum chloride, there are 3 moles of chloride ions. So we can use this information to figure out how many chloride ions there would be in 4.5 moles of aluminum chloride. So if we have 4.5 moles of aluminum chloride, so we're just using the chemical formula, right, as a way to think about the ratio of atoms and the overall molecule, or in this case, formula unit. So we have 4.5 moles of aluminum chloride. For every 1 mole of aluminum chloride, there are 3 moles of chloride ions. So 4.5 times 3 is 13.5. So we have 13.5 moles of aluminum chloride in 4.5, we have 13.5 moles of chloride ions for every 4.5 moles of aluminum chloride that we might start with. Okay, just to summarize, chemical formulas give us a lot of information. Chemical formulas allow us to calculate molar mass. If we have molar mass, we can figure out moles, we can figure out grams, and they also allow us to look at the relative number of atoms in a particular compound, and we can use that information, right, to make ratios to find if we have the moles of a compound, we can find the moles of individual atoms or ions in that particular compound. So it gives us this information that allows us to make relationships or ratios to help us figure other things out, essentially. Okay, so we've talked about molar mass, and we've also talked about looking at the relative moles of atoms in a molecule. One other thing that we can do is we can look at the composition by mass, and so this is the mass percent, right, that we did in class. And so the mass percent is essentially the mass of each element in the compound, and you can find the mass of each element in the compound by taking that, taking the weight of that element, looking to see how many atoms of that element there are, and then dividing it by the formula weight of whatever compound or substance you're interested in. And this would be the same thing if you wanted to calculate the percent composition of anything. I think like a easy example to think about is if you had something like a bag of M&Ms and you dumped them out and you wanted to calculate the percent of, brown M&Ms, the percent of yellow M&Ms, you would count those pieces, right? You would count out how much you had, and then you would divide it by the total number of M&Ms to get the percentages of each one of those. So it's essentially the same thing, but we're doing it with different elements that compose a particular compound. Okay, so let's look at how to use this. we're going to find the mass percent of oxygen in acetic acid. So the mass percent is going to be equal to the mass of oxygen divided by the total mass. There are two oxygens, so we're going to have to multiply, right, the mass of one oxygen by 2. So 16 times 2, right? Oxygen is 13 or 16, and then there's 2 of them. So we have 32 AMU divided by the formula mass of acetic acid. So once we calculate the formula mass of acetic acid, it's 128.8, say 85. And then since this is a percent, we times it by 100. So this is 24.8%. So acetic acid is 24.8% oxygen. Okay, let's look at this next example. This next example says determine the mass of oxygen in a 7.2 gram sample of aluminum sulfate. Okay, you could solve this problem a couple of ways. Since we're talking about mass percent, I'll solve it the mass percent way. But how I would probably solve this problem is I would just set up a unit conversion. I'll actually solve it both ways. So let's solve it the mass percent way. So first, you could find the mass percent of oxygen in aluminum sulfate, and then you could multiply that number by the grams that you have, the 7.2 grams of sample. Or, I'll do it this way first. You could, if you have 7.2 grams of aluminum sulfate, you could find the molar mass, right, of aluminum sulfate. You could find the moles of aluminum sulfate, right? So 1 mole of aluminum sulfate the molar mass is 342.15 grams. Then you could do a mole ratio. You could look at the moles of aluminum sulfate and compare them to the moles of oxygen. So for every 1 mole of aluminum sulfate, there are 12 moles of oxygen. For every 1 mole of oxygen, there are 16 grams of oxygen. So this would give you 4.04 grams of oxygen as the mass of oxygen in that amount of sample. Alternatively, we could do this by mass percent. So we could find the percent of oxygen in aluminum sulfate. So to do this, we would have 16 times 12. This is the weight of oxygen. We have 12 of them in aluminum sulfate. And then divide that by the formula weight of aluminum sulfate. So aluminum sulfate is 56.12% oxygen by mass. So what we could do is then we could say, okay, well, if aluminum sulfate is that much oxygen by mass, if we multiply 7.2 grams of aluminum sulfate by 0.5612, right, which is the proportion of oxygen in aluminum sulfate, we would get the same answer. So it would be 4.04 grams of oxygen. I prefer to solve this kind of problem the top way, but it can be solved the bottom way. I mean, it's the same. You're doing essentially the same thing, but you know, it might be more make more sense to you to solve one way or the other, which is fine. Okay, so let's look at determining a chemical formula from experimental data. So in class we talked about empirical formulas. They're the simplest whole number ratio of atoms in a particular compound. We can find them through elemental analysis. So if we have masses of elements that form during decomposition, or we know that react together to form a compound, from those percentages we can determine the empirical formula. We can also determine the empirical formula through combustion analysis data. Okay, and then just a note, the empirical formula is a ratio of atoms, or a ratio of moles of atoms. It's not a ratio of masses. I don't think anyone's been confused about that, but I just wanted to mention it. Okay, so let's look at an example. All right, well, let's look at the steps, actually, to find an empirical formula. So what we want to do is, if we're given percentages of atoms that make up a compound, we want to assume that we start with 100 grams of that, and we can find the grams. So it's just turning that percent into grams. So if we have 72% carbon, we say, well, we have 72 grams of carbon. And then we want to convert those grams to moles. We do that using the molar mass. And then you would want to write the formula using moles as subscripts. You're going to find the smallest number of moles. And then if they divide evenly, you can essentially, or close to evenly, you round them right to whole numbers. Like if it's 2.99, well, you can round it to 3. But if the mole ratios are in fractions, like 0.5, 0.33, or 0.25, then you need to find a number to make them a whole number. So if it's 0.5, you'd multiply by 2. If it's 0.33, you'd multiply by 3. And if it's 0.25, you'd multiply by 4. Also, if it's 0.75, you'd multiply by 4. So that's how you, those are the steps. So be familiar with those steps. So let's go through this. Okay, so we have a compound that has nitrogen and oxygen. These are in percent, so the first step is to turn them into grams. We can just turn them into grams like this because we assume that we have 100 grams since it was percent. And then we want to find the number of moles of each of these. We do that using the molar mass. Nitrogen's 14.1 grams for every 1 mole of nitrogen. Okay, so we can find the molecular formula from a compound from the empirical formula if we know the molar mass of the compound. So since the empirical formula, right, is the smallest ratio, we can find the whole number multiple, essentially, that we need to go from the empirical to the molecular formula. That's N. And so in order to find N, we can look at the ratio of the molar mass of the compound to the molar mass of the empirical formula. Once we find that, we can use the value of N to find the molecular formula. All right, so let's look at an example of how we might use this. So we have a compound that's 49.48% carbon, 5.19% hydrogen, and 28.85% nitrogen, and 16.48% oxygen. We have the molecular weight. So if we are able to find the empirical formula, we can find the molar mass of that empirical formula. We can take that molar mass and divide it into the molecular weight, and then we'll find how we'll find N, essentially, and then we'll know how to get the molecular formula. So let's do that. So this problem is just like the one that we just did before. You have a percent of an element. You can turn that percent into grams, and then you find the moles. So let's find the moles of everything. I'll start with carbon. 49.48 grams of carbon. Carbon's 12.10 grams for every 1 mole of carbon. I'm just going to set all of these up and then put them in my calculator all at the same time. 5.19 grams of hydrogen, every 1.008 grams of hydrogen. There's 1 mole of hydrogen. There's 28.85 grams of nitrogen, 14 grams of nitrogen for every 1 mole of nitrogen. And 16.48 grams of oxygen. The molecular weight of oxygen. All right, I'm going to calculate all of these. 49.48 divided by 12.01, 4.11. I'm going to keep all of these. 99 moles of carbon, 5.19 divided by 1.008, 5.1488 moles of hydrogen, 28.85 divided by 14.01, 2.059 moles of nitrogen, 16.48 divided by 16, 1.03 moles of oxygen. Okay. So I'm going to write the moles here, 4.1199, 5.1. Okay, so oxygen's the smallest, so I'm going to divide everything by oxygen, moles. I get 3.99999, so this is close enough to 4. And then 5.1488 divided by 103. I get 4.99. This is close enough to 5. .999 for nitrogen. It's close enough to 2, and then there's 1 oxygen. Okay, so we've found our empirical formula. Now that we've found our empirical formula, we want to find the molecular formula. I'm going to put this over here. So, the molecular formula, in order to find the number that we're going to use to find the molecular formula, and we're going to take the molar mass of the compound divided by the molar mass from the empirical formula. So we need to find the molar mass of the empirical formula. We have 4 carbons. We have 5 nitrogens. So I'm just calculating the molar mass right now. Okay, I get the molar mass to be 97.1 grams per mole. The molar mass is 194.19 grams per mole. So I'm going to divide these. Okay, I get 1.99989, so it's approximately 2. So I'm going to multiply each one of these by 2. Right? So carbon is 4 times 2, that's 8. Hydrogen, 5 times 2, 10. Nitrogen, 2 times 2, that's 4. Oxygen, 1 times 2, that's 2. So now we have the molecular formula. Okay, so finally we have combustion analysis, and I want to remind everyone that there's already an example on YouTube of combustion analysis. So for combustion analysis, you can burn something and then you can get carbon dioxide and water produced. You can measure the amount, the mass of carbon dioxide and water, and you can use that information to figure out the empirical formula of your starting material. And usually people do this for organic compounds because they combust pretty easily. They can contain any atoms. The ones we did in class, were with carbon, hydrogen, and oxygen. But you could have other things in there like nitrogen or halogens or something else. But most commonly it's carbon, hydrogen, and oxygen. And then by knowing the amount, the mass of carbon dioxide in water, you can find the moles of carbon dioxide in water. You can use that to find the moles of carbon, the moles of hydrogen, And then if it's something that contains oxygen, then you can use that information to find grams of oxygen and grams of hydrogen, and then you can calculate the grams of oxygen from that. And that's exactly like what we did in class and what the other video on YouTube is like. So let's just look at another example. So you have something that has carbon, hydrogen, and oxygen in it. You start out with 63.8 milligrams of the compound. You get 1.450 milligrams of carbon dioxide and 59.38 milligrams of water. We want to find the empirical formula. We can go from grams of carbon dioxide to moles of carbon. We can go from grams of water to moles of water. That's what we're going to do first. You have 145 milligrams of CO2. So you know that you have to convert this into grams if you want to use the molar mass. So for every 1,000 milligrams, there's 1 gram. The molar mass of carbon dioxide is 44.01 grams of CO2 for every 1 mole of CO2. For every 1 mole of CO2, there's 1 mole of carbon in that molecule. (145) divided by 1,000 divided by 44.01. So it was 0.00329 moles of carbon. All right, 50. I'm going to do the same thing with water. Find hydrogen. 1,000 milligrams of water every put 1,000 milligrams for every 1 gram. All right, so water is 18.02 grams every 1 mole of water. And for every 1 mole of water, there are 2 moles of hydrogen. So let's see what this equals. 59.38 divided by 1,000 divided by 18.02 times 2. Okay, so you have 0.00659 moles of hydrogen. Okay, we have the moles of hydrogen and the moles of carbon. If this was a different combustion analysis problem that didn't contain oxygen, we could go and find the empirical formula right now. Unfortunately, this has oxygen. Since both products, carbon dioxide and water, have oxygen, we can't directly find the moles of oxygen. So we have to use the moles of carbon and the moles of hydrogen to find out the mass of carbon and the mass of hydrogen. We can add those masses together and subtract it from the initial mass. That'll give us the mass of oxygen, and then we can use that to find the moles. So that's what I'm going to do now. Okay, so if we have 0.003295 moles of carbon, for every 1 mole of carbon, there are 12.01 grams carbon. So that gives us 0.0 0.03957 grams of carbon. Let's look at the oxygen, the hydrogen, 0.006590 moles. Of hydrogen. For every 1 mole of hydrogen, there's 1.008 grams of hydrogen. That's 0.00664 grams of hydrogen. Okay, we have our mass of hydrogen and of carbon. Let's add those together and subtract it from the initial mass. Notice something here. These are in grams. Oh. These are in grams. Your initial mass is in milligrams. So let's convert the initial mass in milligrams. So to go from milligrams to grams, you divide by 1,000. So I'm going to put 68.3 divided by 1,000 into my calculator. So 0.0638 grams of the compound. We're going to subtract off the amount of carbon, not the amount, the mass of carbon, and the mass of hydrogen. So we have 0.01759 grams of oxygen. Now that we have our grams of oxygen, we can find moles of oxygen. That's what I'm going to do now. So 0.1, I forgot a 0. 0.01759 grams of oxygen. Oxygen is 16 grams for every 1 mole of oxygen. So we have 0.00199 moles of oxygen. Now we have moles of carbon, moles of hydrogen, and moles of oxygen. So we can find, move this over here, so we can find the empirical formula. So let's do that now. Okay, so carbon, 0.03957, hydrogen 0.0064, and oxygen 0.00199. So oxygen is the smallest, so I'm going to divide everything by that. Oh, I just realized I wrote the mass instead of the moles. I don't see. Alright, I'm going to write that again. So for carbon, the moles that we got, okay, we have 0.00329. Right, and that's the moles of carbon from over there. Hydrogen, we have 0.00659 moles. And then for oxygen, we have 0.001099. So oxygen, right, is still the smallest. So I'm going to divide everything by oxygen still. I just had accidentally before written I took the grams of carbon and I wrote it down here by mistake. But it's supposed to be the moles of carbon, right? Okay, so I get that there are 3 carbons. For hydrogen, I get that there are 6 hydrogens, and for oxygen there's just 1 oxygen. So this is the empirical formula. I know that my handwriting is a little hard to read. My stylus isn't working very well. But in any event, those are all of the steps that you would take in order to determine an empirical formula from a combustion analysis containing oxygen. Okay, the last thing is writing chemical reactions. So remember that reactions involve chemical substances changing into new substances, right? So the way that the atoms are arranged changes. And we write them reactants on the left-hand side, yields, products on the right-hand side. So chemical equations, they're really useful. They give us the formula of the reactants and products. They tell us the state, solid, liquid, gas, aqueous. They tell us the relative numbers of reactant and product. And they can be used to determine the weights of reactants used in products that can be made. So we can find out information about one component using maybe the mass or the number of moles of another. And again, the states are gas, liquid, solid, and aqueous. So aqueous is anytime there's a solution. All right, so let's look at an example. So this one we have C10H12 plus O2 yields water and carbon dioxide. So let's start with carbon. Carbon has 10 on the reactant side, and so we could put 10 on the product side. There are 12 hydrogens. We're starting at this one because it's the most complicated molecule out of all of these. There are 12 hydrogens on the products, the reactant side. We need to find out the hydrogens on the product side. There's 12 over there, and then each water has 2 hydrogens. We can put a 6 over here. Now let's try to deal with the oxygens. So there's 6 on the product side from water, and then 20 from the oxygen and carbon dioxide. So there's 28 oxygen atoms total on the product side. There were 2 on the reactant side. So whatever number we use, we have to be able to multiply it by 2 to get 28. And so that number or 26. So that number is 13. So we'd put a 13 here. So we have 10 carbons on the left-hand side, 10 carbons on the right-hand side, 12 hydrogens on the left-hand side, 12 hydrogens on the right-hand side. We have 26 oxygens on the left-hand side, and now we have 26 on the right-hand side, so our equation is balanced. So let's look at this next one. So we have aluminum acetate reacting with ammonium phosphate to form aluminum phosphate and ammonium acetate. So let's try this. You have to know the names of these things. Aluminum acetate. Aluminum has a 3+ charge. Acetate has a 1- charge. And so you're gonna need 3 acetate for every 1 aluminum. So let's write that Al and then acetate C2H3O2. There are 3 acetates for every 1 aluminum. This is aqueous, so we need to write AQ plus ammonium phosphate. Ammonium is NH4 plus, right? So ammonium has a +1 charge on it. Then you have phosphate. Phosphate is PO4. Phosphate has a -3 charge on it. So what that means is that you're going to need 3 ammoniums for every 1 phosphate. All right, this yields, and I'm going to write the products in a different color. Solid aluminum phosphate. So aluminum phosphate. Aluminum has a 3+ charge. Phosphate has a -3 charge, so they're going to combine in a 1-to-1 ratio. I just saw that I didn't write aqueous before in the reactant, so I'm going to go back and write that. AQ. Alright, so you have the solid aluminum phosphate, and then you're going to have aqueous ammonium acetate. Ammonium comes first, right? It's the thing with the positive charge, the polyatomic ion with a positive charge. It has a +1 charge. Acetate has a -1 charge. So these will go in a 1-to-1 ratio, and it's aqueous. Okay, so let's balance this equation. So let's start with aluminum acetate. Aluminum, there's 1 in the reactants, there's 1 in the products, so we're good there. Let's look at acetate. There's 3 acetates in the reactants, but there's only 1 in the products. So if we put a coefficient 3 here, then we would have 3 acetates on each side. So let's look at ammonium phosphate. There's 3 ammoniums on the reactant side, and there's 3 ammoniums now on the product side. So we have the right number of ammoniums. So then let's look at phosphate. Phosphate in the reactant side, there's just 1. In the product side, there's just 1 too. So everything is balanced now. Alright, so that is the end of all of the review for Chapter 3. Make sure you know how to balance equations from both the equation already written with the formula and then also from the chemical names. Make sure that you can do a combustion analysis kind of problem. Make sure you can convert from empirical to molecular formulas, that you can do percent mass, and you can find molecular masses or molar masses for different compounds and look at the mole ratio within a compound to find out information, right? So to look at the chemical formula, either to find the molar mass or the ratio of moles of one atom or element to the compound as a whole.